ballistic services, cutting, things like that. We have full service electric line logging for production logging, casing evaluation, etc. And we also have advanced conveyance systems like our carbon pod system, with certain areas of practice. And we have operations pretty much globally. We are active in North America and South America, and all over Europe, Africa, and into Asia. We have main bases in Norway. We have the operations base in Malaysia, and we do a lot of other work on a suitcase basis where we just provide the tools. So, specifically on electromagnetic techniques, there are a number of methods for evaluating corrosion downhole using magnetic techniques. Flux leakage is the first one. It uses a permanent magnetic field, and it allows you to get the corrosion profile of a single tubular, and you can discriminate between internal and external defects. What it doesn't do is give you an absolute thickness of the metal. It can just give you an idea of the change, so you can see pitting and corrosion, and it's only for the first string. If we move on to eddy current techniques, there are two different types of that, the near field and the remote field. The near field uses quite a high frequency alternating magnetic field. It doesn't have much penetration, and it gives you information on the first string only, so the tubing that the tool is inside, and it can let you discriminate between internal and external defects. Remote field eddy current uses a lower frequency, but again alternating magnetic field. It has much higher penetration, and it will give you average thickness of the first and the second strings, so long as they're not too large. But there is another technique called pulsed eddy current, which again uses an alternating magnetic field, but it's different type. It's not sinusoidal, and we record in the time domain. So it gives us much higher penetration. It gives us the average thickness, and because of the techniques that we use, we're able to evaluate multiple barriers, up to 4 in the case of the particular tool I'm going to talk about today. So we can, in a single run in the hole, evaluate metal loss in up to 4 concentric strings. And we can generate the thickness from there, and we can get an idea of corrosion. So the tool is capable of doing a full analysis of 4 barriers in one run. And because of that, we can do time-lapse metal loss. So we can run a log, and then we can go back sometime later, run a log again, and get an idea of the rate of corrosion that is occurring even in exterior barriers. So how it works is quite simple. We have a transmitter and a receiver coil, and they are wound in the same core, so they are co-located. And what we do is apply a square wave signal to the transmitter. So we provide that square wave to it. That creates a magnetic field which magnetizes the tubular surrounding it. We then record with the receiver coil the decay of the electromotive force. So when the magnetic field collapses, it creates a current and creates another field which we detect as an electromotive force, voltage, essentially. And the number of barriers that we can investigate, so the number of tubing strings and casing strings, depends on the duration of the recording. So if we look at that in slightly more detail, the transmitter pulse is a certain duration in time. The short probe, and we have 2 probes in the tool, the short probe is for 120 milliseconds, and the long probe is longer at 300 milliseconds. Then we record the decay of the receiver. So we actually record the way that the voltage drops at the receiver coil against time. And again, the short probe is for 180 milliseconds, and the long probe is up to 360. So the reason we do this is to analyze multiple strings in one go. So the early time, close to when you switch the transmitter off, we're looking at the inner strings. So they'll be the tubing and the first casing. The later time, we're looking for the outer strings. So that would be the third and the fourth barriers. And we can go up to quite large casing sizes on the outside. So this is an actual plot of a test of the coils themselves, and we're showing two curves for each of the short and the long coils. So the barriers, as I mentioned, are the information from the barriers depend on where they are in the decay curve. So early time, we're looking for the first barrier. Slightly later on is where we get the information from the second barrier. The third barrier is even further out in time, and the fourth barrier is the last place that we look at. So for the short space, for the short probe, if this is a test where there's 3 barriers and 4 barriers. So the 3 barrier decay looks like that, and the 4 barrier is very, very similar. And this is showing that the short coil and the near time arrivals have very little, are not affected by the exterior casing. The other side of it is on the long probe, we have the 3 barrier decay and the 4 barrier decay, and they are quite similar until you get further out, and then there's a divergence in there, and that's how we can discriminate between the signal from the 4th barrier and the 3rd barrier, and that's why we need to record such a long time of the decay. So each decay curve has 54 readings in it, so we get good resolution and we can reconstruct the decay curve. And then we need to solve that for the thickness of the metal that is remaining. So the thickness calculation. For a single string, it's quite straightforward. We use Faraday's law. So we're trying to find the thickness of the tubular. We need to know the magnetic permeability of the tubing. So we know the material of it, we know the magnetic permeability. We need to know the electric conductivity, because the current that's induced in it is going to depend on the conductivity of the metal. We need to know what the outer diameter of the tubular is nominally, because that affects the geometry. And we need to know what the well temperature is, because the temperature affects the other parameters. So we know the magnetic permeability, the conductivity, the nominal OD, and the temperature, because we have a temperature probe in the tool. So we measure the electromotive force from the decay curve at the 54 points along the time. So we can calculate the thickness from an equation that's a function of the thickness, the permeability, the conductivity, the diameter, and the temperature. So it's fairly straightforward to solve. It gets a little more complicated when we have more than one string. So in the example for a dual string, we now have 2 thicknesses we want to calculate. We've got 2 magnetic permeabilities, 2 conductivities, and these are very likely to be the same if the casing and the tubing are the same grade and same composition of metal. The 2 diameters of the inner and the outer tubular, we know what the well temperature is. So knowing all of those parameters and measuring the decay curve, again, we can calculate both of the thicknesses. But there's an addition here, there's the correction coefficient to account for the relative positions of the tubulars within themselves. So there is a correction factor in there. But again, we can solve for 2 strings. So if we move on to 4, then it's exactly the same kind of scenario, except now we have 4 unknowns that we are trying to find. We've got 4 magnetic permeabilities, 4 conductivities, 4 ODs. We still have the same well temperature, and the EMF is measured from the decay curve, and that is a function of all of the parameters. So it gets quite complicated, but we can derive the individual thicknesses from the decay curve and where the the voltage is actually measured within that decay curve. So what we have here is an equation to give us the 4 thicknesses. So at each depth interval, the metal thickness of each barrier is determined. This thickness is very important to remember, is an average over the entire circumference. So it's an average thickness of all the metal over that depth sample. So if we have defects like 100% penetration, like a hole, that's going to be averaged into the circumference value. So if we have an unwrapped section of tubing, that's like the depth sample that we're looking at, that's cut down one side and folded out flat. If we've got 0 metal loss, so we've got 100% of the metal mass, then we get a thickness from that. If we put a hole in that tubing, equating to 10% of the total metal loss of that depth sample, 90% metal mass, that hole, it may go all the way through, but it's going to be averaged out into the reading. So that would it's very important to remember that looking at the results from these logs, because a 10% metal loss, it may be a hole, but equally it may be a slight thinning of the tubing all the way around. So you need to look at the context and the other parameters. So that's a bit about the theory of the tool. So moving on to the specific of the tool itself, the tool specifications. It has a gamma ray and pressure sensor built in, as well as the temperature sensor, which is important for analysis. We've got 2 sensors, a short one and a long one, and the electronics. And we have centralizers that can be fitted in there. There's no specific well fluids that we need for operation, or all normal well fluids are fine. Brines, produce water, oil, gas, they're all fine. We can operate in deviated or horizontal wells with the centralizers in there, and we log it real time in surface readout on the monoconductor wireline. The maximum OD is 1.65 inches, so slightly less than 1/11/16, and it's about 3.6 meters long total, including the centralizers, and is very light at 14 kilos. So the maximum pressure is 15,000 psi and 150 C, and this will do 4 barriers. So the operating envelope is from 2.5 inches up to 20 inches, and the amount of metal, the total thickness that we can accurately measure, depends on how many barriers there are. So if we have if we're only looking at 1 barrier, then we can go up to 0.6 of an inch. 4 barriers, the total cumulative thickness that we can do is 1.9 inches. The accuracy of each of the measurements decreases slightly because of the more uncertainty as we go out with more barriers. So we have to also bear in mind that when we're looking at the interpretation. So once we've acquired this data, then we need to know what to do with it. So the answer product is very important. So the first answer product we offer is the raw data API plot. So after we've logged, we generate the API standard plot of the raw data with all of the raw data sensor information on it. Then we generate LAS raw files of the individual data curves. Then after we've done the processing of the thickness, then we provide those curves as well. Once we have the thickness, we then start to move on to some more of the analysis displays. So we have what we call pipe view, which is a graphical display of areas of metal loss or buildup. And we do a full written thickness report afterwards, where we go into things in more detail. So the raw data plots can be very, very informative. So this is an example of what we're looking at. This is a section of log where we're going from 4 barriers at the top. So we've got 13 3/8, 9 5/8, 7-inch and tubing inside. This is the casing shoe that's marked on there. And then below there, we have the 3 barriers, 9 5/8, 7-inch and tubing. So as mentioned before, the close time, the near time, the early arrivals are affected by the inner strings. So up at the top, you can see these early arrivals are absolutely unaffected by the change in casing. So the 13 3/8 casing shoe below there, the signal is exactly the same as above. So we're seeing that the effect from here is from the inner strings. As we go further to the right, we go further out in time, and we start to see a change in the signal that we're getting on the later time arrivals. And the signals are getting larger. They're being delayed in their decay. That's an indication of more metal mass. So that corresponds to where the casing shoe is. So above this point, we have a higher signal. Below, we have a lower signal. And that is directly related to how much metal there is there. So we can see very clearly, and this is part of the QC that we do, the quality control, to make sure that we're actually reading correctly. So below here, you can still pick out the 7-inch collars. There's a tubing collar and a 9 5/8 collar right on top of each other. Tubing collar and the 7-inch and the 9 5/8 are on top of each other again. But we can discriminate all of those. So we have another example of the long coil. We have, this is showing a casing weight change. So it's not like a casing shoe. It happens at this point, at this collar here. Above there, we have slightly heavier weight casing. Below it, we have slightly lighter weight casing. And the baseline is shifted. It's not shifted very much, but we can, of course, zoom in on this and look at it in more detail. And it's quite clear to see that there is a change in the metal mass and hence the thickness at this point. And again, we can see all the other features. We can see the tubing, the 7-inch, and the 9 5/8 collars all over the place. So here's another example, which is in the same well, in a slightly different place. Can we keep the questions to the end, or would you prefer that I do reply as we go along?
We can keep it at the end.
Yeah. Okay. Cool. So the raw data that we're looking at here, we can see the normal collars that we see, but there's obviously a very large feature here. This is something going on at this point in the log, and this is actually a diverter, a stage collar for cementing in the 7-inch, and that is relatively has a lot more metal mass in it. It's OD and it's got sleeves and things, and that shows up as a much increased signal going through here. So again, we know where the diverter is, we know where the 7-inch DV is. So this is another quality control method that we can see. So what I'd like to show now is a comparison between the short coil and the long coil. This is going through a section where we've got an expansion joint in tubing, and then we've got a packer, and we have 9 5/8 and 7-inch on the outside. The first thing you see is that the short coil response looks much spikier, and that's because the shorter the coil, the better your vertical resolution. So we can use the short coil to look at the near arrivals, the tubing and the first casing string, and get slightly better vertical resolution. But again, we can pick out all of the features, tubing collars, and the expansion joint shows up quite well, so we can actually see whether it's at what stage of the travel it's at. The long coil again also picks up everything, shows the difference between in the expansion joint, but the resolution is not quite so good. But also here, the packer shows up very well, as it does on the short coil, but the packer is very, very much more massive in terms of metal. So it actually shows up as a much larger signal. So when we come to the entry guide on the tubing, we can see on both the long and the short, there's a huge decrease in the signal because the mass of the tubing has disappeared, and we're down to only 2 strings through this section here. But we can still see the 7-inch and the 9 5/8 collars on both of them. But we can see them generally on the short coil where we don't when there are other tubing strings in the way. So again, that's an indication of where we need to look in the time decay to get the collars. And then we're going into the bottom here to a packer with a tubing hanger. This is into a 5-inch liner. Sorry, a liner hanger. So we can see as we come down through all the bits and pieces of the packer and then into the 5-inch collar. So that gives us a different baseline. So again, if we log one of these tools through a complex completion, we are able to go through and identify just from the raw data all of the individual completion items and use that for quality control, depth control, and to look for any immediate problems with gross features. So we look at a section of log here. This is another one, short probe on the left, long probe on the right, and going through a section of log. So after we've processed it, this is the pipe view over the same interval that we just looked at. So we have at this point the 4 barriers. We've got the well sketch in the middle, the 4 barriers, and their mirror images on one side and the other. So we've got the closest one is the first barrier, so that's the tubing, then the second barrier, third barrier, fourth barrier. The green is where the nominal, the metal calculated is larger than nominal, and the red is lower than nominal. And so the green is higher than nominal, that's a tubing joint. So we can see this is the collar, which has more metal in there, so we can pick out the collars very easily by looking at these curves. The red is where it's below nominal, so there's some amount of metal loss compared to nominal. Of course, if you do a time lapse, then you reference the metal loss or gain to the previous pass. So here in the tubing, there's very little going on. There's no metal loss, everything looks okay. The second barrier out, we have a little bit of metal loss up in the top section, but we have lower down, we have this section here. And this is starting to show that there's a bit of corrosion and a bit of metal loss in this specific place. If we move out to the third barrier, then we can see that there is an area where there is definite metal loss. It gets a bit bigger and then it goes out. Now, this is why looking at these particular plots, you need to bear in mind the way that the tool averages the thickness. So this is not showing complete penetration, it's not showing complete metal loss, but that may be an indication of an actual hole. So if we then look out at the string behind that, or this is the exterior string, 13 3/8 I believe in this case, we can actually see there is a huge amount, and the thickness calculation shows that there is a hole there. This goes all the way through, so it's showing that there is pretty much, nothing. There is definitely a hole through at this point, which makes it very likely that this may actually be a hole here because we're getting corrosion at exactly the same depth on the string inside it. So this is an indication in the way we look at the logs to say that we've got serious corrosion on the outside, which is very likely to have caused enough corrosion for a hole on this one, and it's starting to come through here. So this would be an indication that there is a problem with the envelope of the well. So the way we can report the data, we can do the full statistical analysis. So we can present that in various different ways, either with absolute thickness, metal loss, percentages, etc. So we can do this individually for the first barrier, second barrier, third barrier, etc. So we can present this in many different ways. And for the for the detailed reports, we come in with kind of the overview views. So we have a schematic with the well barrier presented on there, and then we mark on there areas where there is anything of interest that's shown up in the interpretation. So here we can look at where there is potential problems on the outside, so we can see exactly where everything is within the well barrier envelope. And we can present that in various ways. In pipe view, we can zoom in on particular barriers and present other data. So we can give kind of overview of all the most important points. But we also, as part of the interpretation, we go through and do more detailed analysis on every feature that we see and all items. So here we can look in more detail at the side pockets. There are a crossover, which we would go to in detail, and we do analysis on all of these. We generate plots for all of the features that we come across, and we can actually look at the we do the calibration. We present all the calibration information for trackability, etc. as well. So to move on to a quick example. This is an example of field-wide monitoring. This is an onshore field in the Middle East region. So the field is quite old. It was originally developed in the 40s. And we have surveyed to date 30 wells in this field. The oldest was drilled in 1976, and the newest was in 2013. In this field, there are two types of completion, some of them with 4 barriers, some with 5, and very different arrangements of casings, liners, etc. There are also 2 different well types. Some are injectors, some are producers. The reservoir types completed are gas and oil, and there are a mixture of gas injectors, gas lift producers, oil producers, and gas producers. So there are a variety of slightly different well types. So if we look at all of the barriers together, this is in the 4th barrier, which is 13/3/8, and this was we've done these for all of the other barriers as well, of course, but the specific objectives of these surveys is to establish what the integrity of the exterior barrier, like the first barrier against formation of these wells is. So if we plot all of the data together, and we've got the metal loss percentage up on the y-axis, the x-axis is the age in years. So there is a definite trend line of increasing corrosion against age, which is what you'd kind of expect. We also have the 3 outliers at the top, where we have 100% metal loss, showing that it's been breached with a hole already. But it's also useful with this kind of data to sort it by the sector. There are 3 different sectors in this particular field. So if we look at the first one, these are some of the slightly older wells, and there is again a definite trend in the age and the amount of corrosion that we're seeing, and there are these 2 outliers as well. The second area that we look at, the second sector, is showing again a trend, a profile of corrosion against time, against the depth. And it's straight away we can see that these are some of the newer wells, and they seem to be corroding at a faster rate than the older wells in the different area. And again, this is one of the areas where we have the outlier, where we have a complete hole in there. And then the third area is showing again an increasing trend against time, but it's much lower than either of the other 2. So by using the data in this kind of way, it gives us the capability to monitor the envelope, the integrity envelope of the well, and we can do it over time in a couple of ways. We can do time lapse, so we actually log the same thing twice and get an absolute idea of the rate of corrosion, or we can survey a number of wells in the field and then reference that back to when they've been completed, how long they've been in operation. So to just do a bit of results validation, here's a log that was done. There's a 7-inch scab liner installed with a couple of strings outside it. So over here, and this is these are the two exterior strings. This one is the furthest out. This one is the center one, and the curve on the left here is the scab liner results. So there's extensive corrosion of the second and third barriers. So there is an awful lot of corrosion here on the outside. So we might expect something to be going on here. The scab liner, we can see there's an awful lot of corrosion there, and we get responses like this, where we can see there's almost complete loss of signal, which is showing a complete loss of metal at that point. So when the scab liner was actually retrieved, it parted, and there were some pictures taken of the liner itself. So this is actually a very good validation of the results and the interpretation acquired in the downhole environment. So it's a nice way of showing that the tool and the processing are actually robust enough, and we have a high confidence in the accuracy. So just to sum up, we have what we call the MIDS4, which is the 4-string version of this tool. It's an industry standard technique. The pulsed eddy current is a accepted technique for thickness evaluation of concentric strings, multiple strings. It's simple, it's reliable. We can apply analysis to it at appropriate levels. So we can just we can look at the raw data just for overview, and then we can go into far more detailed analysis, and we can evaluate tubing and casing. The deliverables are supported by, we have a global analyst team, so we can provide 24/7 response for this. We have broad experience of different areas and different interpretation. And of course, the field personnel and the tool would be available in the country that we're operating in. So the table at the bottom is just an idea of the turnaround time for the specific answer products. So any major anomalies we'll spot from the raw data, and we do that fairly quickly. And then we can present the raw data, and then after that we start presenting the pipe view, with thickness calculations, and we can do the full statistical analysis with the report and everything in there in details within 2 weeks of receiving the data. So I think that kind of concludes the overview. So I noticed there are quite a few questions being asked there, so if we can move on to those.
Okay, Duncan. So basically, there are 2 questions in the chat room. So if I may, or you can read it. Basically, okay. I think for the first one, it is from Shahmin. How can you explain again on one kind of parameter? Is it about accuracy? I think this is regarding the accuracy table that we showed.
Okay, the accuracy. This one.
Yes.
Yeah. So the length of crack, the accuracy is it's a percentage of the nominal thickness. So it gets progressively slightly worse the more barriers we have. So the 4th barrier, if we're measuring that through 3 other pipes, then the accuracy is plus or minus 20%. It's 20% of the the nominal thickness of that fourth barrier. The crack that we look at, if there is a crack in the, as opposed to a hole or generalized corrosion, but if there's a crack, a physical crack in the tubular itself, the length of that crack that we can resolve down to depends on the which barrier we're looking at. So if we're looking for the first barrier, the tubing, if we look at the circumferential perimeter of it, the circumferential length, around the circumference of that tubing, if there's a crack of 1/9 of that particular circumferential length, then we will detect that. If it's less than 1/9, we won't necessarily pick it up. So if it's more than 1/9, we will, and so on out to the fourth barrier. So in the fourth barrier, it needs to be quite a large crack, quite a long crack, before we can actually detect it. And the reason we specify that separately is because of the way the tool works. A crack can be quite hard to detect. If it's vertical, along the axis of the well, it's much easier to detect because it interrupts the current path that's introduced, so we can see that easier. Okay, does that answer it?
Is that answering your question, TP? All right. I think you can speak. I mute you.
Hello?
Yes, we can hear you.
All right. Okay. I think it's clear now. All right.
Okay, cool.
All right.
But it will be appreciated that Archer can so-called predetermine that, for example, if we are intervening in 3.5 tubing, so once overnight, those parameters can be so-called pre-calculated earlier, then we know that that's the so-called minimum crack that can be detected by these tools.
I'm sorry, so you're saying that I didn't quite catch the question, sorry.
It's okay. It's about just about calibration between tubing so-called circumference with this minimum crack that need to be validated. Yeah.
Yeah, it depends on the size of the tubing that we're looking at.
All right. Okay.
Yeah.
Okay. There are also other questions from Darren. You're referring to slide number 26.
26.
21, sorry. We go to slide 21.
21. That one.
Yeah. The red area indicate tubing area?
The red area indicates where the thickness was calculated at less than nominal.
Hello. Yeah. Hello. Can you hear me?
Yes.
Yeah. So the red area indicated, the nominal area, but it's indicating on the tubing side or the beyond the tubing, which is reading at the production casing.
On this particular, you're talking about the right-hand pipe view plot.
Yeah.
Yeah. Okay. What we've got there is that's the thickness. The curve on either side of the well sketch that is specifically only for the tubing. So the green section is where there's more. It's bigger than nominal calculated. So that's the collar. And then so we just reference the nominal thickness of that particular grade of tubing, and if the thickness calculated is below that, we shade it red. So that's on the thickness side of it in inches, in absolute inches. The other one on the right is the percentage metal loss. So that's more of a volumetric based on the thickness change rather than the actual thickness of it. So that's in a percentage. The one that's the one that's either side of the well sketch is absolute thickness in inches. The one on the right is a percentage of the total metal volume that's gone.
Okay.
Then also I have another question from second slide 26.
Slide
Yep.
26.
Yeah. So as the age getting older, why 100% metal loss in 23rd year, then following year show less than 100%?
Sorry, can you repeat that?
As the age getting older, why 100% metal loss in 23rd year, and then the following year show less than 100%?
This is a plot of, these are not all the same wells. This is individual wells. So the age along the bottom is the time from when the well was first drilled, that particular well. So, for example, at 23 years, or 22 years, we have this particular well up at the top showed 100% metal loss in the 13/3/8. We don't know when that actually occurred because, you know, each of these wells has only been logged once. So this is not cumulative time lapse on one well. This is all the different wells in the sector.
Okay.
So essentially, what we have here, these outliers at the top, where we've got complete metal loss, these are actually related to particular very shallow aquifers that are very corrosive, which go all the way over the Middle East. And sometimes when particular wells are drilled and completed, they may have problems with them. So they may have very poor cementing through those aquifer zones. And in those particular wells, if they weren't completed properly, then they can get accelerated corrosion compared to the others.
So it means that each spot highlighted here is respective individual well.
Correct.
Okay.
Yeah. So it's each individual well plotted against how long they've actually been in operation.
Okay.
So it is not time lapse, it's actually the age of the well itself.
It is the age of the well. Time-lapse logging, the operator here is planning to start doing time-lapse logging on repeating it on specific wells, but at the moment their focus is to actually log all of the wells they've got so they can see which ones have big problems. Then they will start doing the specific well time lapses to get more accurate rates of corrosion.
Okay.
Okay. Also, there's one question from Zulfarhan bin Ibrahim. Hi Duncan, on the pipe view plots, greater than nominal could only indicate colors, or will it measure any constrictions or clogs?
Constrictions or what?
Clogging. C-L-O-G.
It's clogging.
Yeah. If I want to.
Yeah. I mean, there are. It needs to be a magnetic and conductive deposit on there. Mostly, what we will see, we can see the collars. But if there is, some slight areas where it seems more than nominal, that's generally accounted for by the variation in manufacture, because the casing is specified. The OD is specified as 13/3/8 whatever, plus or minus a little bit, and the thickness is also specified with a plus or minus tolerance on it. So if we just use the nominal, some joints may have areas where it is slightly heavier. So that's generally what we will see. I don't know if that answered the question or not.
Okay. Then
Okay.
we go to the next question. So Farhan, is it okay? Great. So we go to the next question by.
Yeah, I think okay. Okay.
Okay. from Mura Ditran. So is this same as how we do intelligent pigging and MIT?
I'm sorry, say that again?
Is this the same? Is this technology the same as how we do intelligent pigging and also multi-finger caliper?
Well, it's not the same as multi-finger caliper because the multi-finger caliper is inspecting only the inside of the tubing or the first casing string, whatever the fingers are touching. So what you get is an interior profile. What you don't get is any indication of whether there may be external corrosion and the absolute thickness. So with a caliper, with a multi-finger caliper, you're assuming that the exterior is okay for any of your calculations on the remaining thickness. Intelligent pigging, I'm not entirely familiar with. I assume that's for surface pipelines and things. But if you have an intelligent pig with a caliper type arrangement on there, or potentially some sort of magnetic flux leakage device or something like that, then it would be working in broadly the same way. But I'm not aware of intelligent pigging that does multiple concentric barriers.
Okay, great. And then from the same person, can this metal loss show difference between erosion and corrosion?
That's a very good question, and I think the answer is probably no, depending on your definition of erosion and corrosion. For something to be erosion as opposed to corrosion, then there needs to be sustained flow. So to define it that way, if you've got erosion, like you would get potentially in tubing above joints where you've got turbulent flow, you can get ring corrosion above there. So if it's on an exterior string, it's very likely to be corrosion rather than erosion, unless you've got a lot of cross flow going on. But to answer the question in a roundabout way, the tool does not discriminate between what might be inside or outside. What it does is give you an average thickness.
And we have also a question from Zahil. Does casing eccentricity affect the result?
Yes, the reading that you get at the tool is going to depend on the casing strings, the tubing and casing strings, and their relative position to each other. And there are various mathematical techniques that are used to derive the correction factors for those, as I showed in the theory section with the function equation. So yes, they do. It does make a difference that is corrected for, but it's not a massive difference within the relative position of it inside of each other, because the current paths when they're induced, they actually flow around each individual tubular. So there is correction needed, but it's not like an order of magnitude correction. There's some very complex mathematics used to solve them.
Another question from Mr. Sharil. What is the accuracy difference with the tubular with eccentricity issue?
The accuracies that we quote are based on the fact that the four strings are never going to be perfectly concentric. So the accuracy actually takes into account the degree of eccentricity that you may have.
Answering your question, Mr. Sharil.
Hello?
Yes, we can hear you.
But if, for example, if the so-called the tubings, the first barrier and second barrier have so-called straight line eccentrics, comparing to the ones that are having very severe eccentrical issues. So what's the accuracy difference between those reading? Have you simulated that?
Yeah, it's been simulated in the lab with various different degrees of eccentricity in all of these cases, and there's a kind of matrix array approach for the mathematics to solve that sort of in an iterative approach. It's very well modeled mathematically. So that's why the accuracies that we quote are taking into account all of the possible configurations of the strings within each other.
Okay, so basically that's why you put 5% so-called accuracy difference on the first barrier.
Yeah. Because
of these eccentric issues.
Yeah, and when you go out to the second string, it increases because it increases your uncertainty, and then onto the third string, it also increases the range of potential configurations as well.
Okay. Okay. All right.
We move on to another question from Mr. Bernard. This tool can detect thickness change up to how many casing strings?
We do 4 barriers with this particular tool. So we can do tubing and 3 casing strings or 4 casing strings. We can, under some circumstances, detect the presence or not presence of a 5th barrier. So if you've got like the configuration that I showed on some of the wells that we logged in the Middle East, there is a 5th barrier on the outside. Now, we can tell from some of the very late signals that there may be something there, a change in the response. So we could qualitatively say that barrier is there or not, but we don't have enough resolution on there to generate a thickness for that 5th barrier. So at the moment, we do 4 with this tool.
For how the maximum size?
We can go out to 20-inch casing.
Great. So next question from Arif. How do you log in dual string tubings?
We can log in dual string tubing, and what we would prefer to do is actually log both strings. So we'd log the long string all the way up, and also go into the bottom of the short string and log that. The reason we do that is because if you're in the long string, for example, the current paths are going to go around the tubing that you're in, the long string, and the casing on the outside. There will be very little effect from the short string that's in there. So if we want to get all of them together, the long string, all of the casings, and the short string, we have to log the short string as well at the same time. So we would have to do both, log in both the long and the short for full evaluation.
Is that answering your question?
Yep, clear.
Right, all right, great. Okay, there is another question from Wahi. Any limitation on type of material, especially non-magnetic, such as complex and nickel-based alloy?
Yeah, there are limitations. It needs to be magnetic and it needs to be conductive. If you've got, like standard, L80 carbon steel, something like that, then there is no issue at all. As soon as you start getting higher alloys, if you've got nickel and chrome reducing the magnetic properties, then the response is suppressed. However, having said that, most of the up to 25 chrome and things like that, even a bit higher than that, there's enough residual magnetic permeability and certainly conductivity to allow us to measure. The signal to noise ratio goes down a little bit, but we can still do that so long as they're not like completely non-magnetic Monels or something like that.
Okay. Let's last one. I mean, screening all other questions, if any. So as for the chat room, there is no other questions unless there is any additional question from the participants that you want to speak it up. Any other questions from fellow participants for today's session? Because we have already answered some questions. I mean, all questions from the chat room. Is there any more that you want to highlight?
I have no further questions. Thank you.
Well, if there's no further questions from our end, thank you very much for participation. Like what I said earlier, this is one of the many series that we have actually planned. Like several other technology that we plan to share as well. And Ain, will keep in touch with the team, and he will share the links that we intend to do for future sessions itself. If there's no other questions, then thank you very much, team. Anything else, or Duncan?
We have a couple of questions from Zahid.
Okay.
Is the tool ready for Malaysia market?
Ready in what way? I believe we have tools in Norway at the moment which are in the process of being shipped to Malaysia, I believe. So yeah, I would say the tools are ready for market.
So from Wahidullah Wahi, perhaps you can explain what you were trying to say, because you mentioned about we had some tubing leak issue even on for duplex.
I'm sorry, I didn't understand that question.
So now I think gone already. He's left already the meeting.
Okay.
Yeah, I think that's all. Satish, back to you.
Yeah, thank you very much, all. Thank you very much. I see Ponsaril have asked if we can use a different platform. Certainly, we will look at it. There'll be more and more sharing. Thank you very much for the support, and we will continue to share knowledge from our end as well, Tuan and Puan in the session today. Thank you.
Okay.
Yeah, our contact details are there. So just in case if you wanted to contact us, please feel free to take a snapshot, and Ian can share our contact details as well if need be. Thank you very much.
Thank you very much. Thank you for your time. Thank you.
Okay, thank you.
We urgent and happy Ramadan for all those who will celebrate it starting tonight. It's wrap up and we will adjourn the session now. Thank you very much again. Selamat berpuasa.
Okay, thank you all.
Okay, Duncan, thank you very much for your time.
Okay, I think that went well. If there's any other questions, just have them, email them to me. I think there were some good questions there.
Yep. And just to head you up, we're planning also, as Satish mentioned, we try to make few series, and we will share with you with the plan so that we can have a prepare for that. Yeah. So next week or as fast as next week, we plan for a space. So we'll share you details and any plans ahead.
Yeah.
All right. Thank you very much. Bye.
Okay. Okay. Cheers, then.
Yeah.
Okay.
Thank you, Ma.